So for this part of the course, we will try to learn again another techniques, okay? Other techniques and determining whether a given series is convergent or divergent. So let us again recall all the series tests that we know so far. Definition. Series is convergent if the sequence of partial sums Sk is convergent. Otherwise, the series is divergent. And then we have the divergence test. If the limit of an as n approaches infinity is not equal to 0, the series is divergent. And again, let me remind you that if the limit of the terms as n approaches infinity is equal to 0, we don't have a conclusion. And then we also learned integral test. We have a series with non-negative terms. We have a function that is continuous, positive, decreasing, and such that fn equals the terms an. Then the series is convergent if the improper integral converges. The series diverges if the improper integral diverges. And again, this interval here can be replaced by other intervals, k up to plus infinity for some k greater than or equal to 1, which means you just need to check the continuity on this interval, the positivity on this interval, the decreasingness on this interval, and of course, this guy here will be changed to k. But same conclusion. You will get the same conclusion. And then just earlier, we had the comparison test. We have two series, an and series bn here with non-negative terms. If an is less than or equal to bn and the series bn is convergent, then the series an is also convergent. If the bigger series is convergent, then the smaller series will also be convergent. If an is greater than or equal to bn and the series bn is divergent, then the series an is also divergent. So if the smaller series is divergent, the bigger series is forced to be divergent. So this is the comparison test. And then we have the limit comparison test, where we don't need to know which terms are bigger and which terms are smaller. So in here you have the series an and the series bn, again with positive terms. If the limit of an over bn it's a constant, it's a positive constant, then both series converge or both series diverge. They will have the same conclusion. Okay? Now, so far on the test here, the integral test, comparison test, limit comparison test, we were only studying series with positive terms or non-negative terms. Starting this session, we will consider also negative terms. Let us have the following type of series. Alternating series. This series is a series whose terms alternately positive and negative. So you have a series whose terms are alternately positive and negative. So it could be of this form. The sum from n equals 1 up to plus infinity of negative 1 to the n bn, or the sum from n equals 1 to plus infinity of negative 1 raised to n minus 1 bn. where here our Bn, they are positive for all n. So any of the two, you can write them either this way or this way. For this guy here, the term starts with a negative number. Negative 1 raised to 1, that's negative. For this here, the term starts with a positive number. Negative 1 raised to n minus 1, or negative 1 raised to 1 minus 1, that's positive 1. So any of the two, either you start with negative or start with start with positive, the terms must alternate. Positive, negative, positive, negative. Okay? Now, if we have an alternating series, we can easily determine whether it is convergent or divergent. Okay? Let's have some examples for this alternating series. This series here, it's an alternating series. The sum negative 1 to the n times n, and running from 1 up to plus infinity. So this is minus 1, plus 2, minus 3, plus 4, minus 5, etc. We also have this sum n equals 1 to plus infinity of negative 1 raised to n minus 1 over n. So you have here 1 minus 1 half plus 1/3 minus 1/4. Sorry about this. So let me change that. So should be 1/4 there. Okay. So we call this series the alternating harmonic series. It's a harmonic series, but the terms alternate. Alternating harmonic series. Now, for a given alternating series, we use the following test. This is called the alternating series test. Okay? So, if a given alternating series, so let me just write here the alternating series that we have. Either you have negative 1 to the n bn, n starts from 1 up to plus infinity, or you have negative 1 raised to n minus 1 bn, and starting from 1 up to plus infinity. If a given alternating series satisfies this, bn plus 1 less than or equal to bn, this means that these terms here, okay, it's decreasing, okay, and the limit of bn as n approaches infinity, it's equal to 0. So it is not only decreasing, but it goes to 0. Then the series is convergent. Okay? So if you have this, you collect those terms. If you found that it is decreasing and it goes to 0, the series is convergent. Okay? So it's a very easy test. Now, may I remark that if at least one of these fails, the series will diverge. You can use divergence test from there. Okay? You can use divergence test from there. The limit will not exist. The limit, I mean this guy here, or even if you combine this, the limit will not exist. Therefore, divergent by divergence test. So the remark, it's not written here because you actually use a different test. Okay? So again, alternating series test, you have alternating series, these terms here, it's a decreasing sequence, and the limit goes to 0, then the series is convergent. Okay? Let's use this newly discussed test. Show that the alternating harmonic series is convergent. Okay? So first, your Bn, that's your 1 over n. So observe, well, since n, this is less than n plus 1, you will have 1 over n plus 1 less than 1 over n for all n greater than or equal to 1. So Bn plus 1 less than Bn for all n greater than or equal to 1. Meaning the sequence is decreasing. Number 2, obviously, the limit of 1 over n as n approaches plus infinity, this is equal to 0. So by alternating series test, the alternating harmonic series, negative 1 raised to n minus 1 over n, and from 1 up to plus infinity, this is convergent. Okay? Very easy to use, alternating series test. Then again, this only works for alternating series. So you have to take note of that. Next, determine whether the alternating series negative 1 to the n squared over n squared plus 1 converges or diverges. So this is alternating series. Okay? Solution. If you try to look at this, if you try to look at Bn, your Bn would be n squared over n squared plus 1. Okay? And if you get the limit of Bn as n approaches plus infinity, so this is just the limit of n squared over n squared plus 1. As n approaches infinity, this is equal to 1. So the alternating series test fails. Okay? So how do we say, why can we conclude that this series here is divergent? Look, for n, for even integers n, the limit as n approaches infinity, passing through, take note of that, passing through even integers only, okay? Negative 1 to the n squared over n squared plus 1, this is equal to 1. For odd integers, n, if you get the limit as n approaches plus infinity, negative 1 to the n squared over n squared plus 1, meaning passing through odd integers only, the limit will be equal to negative 1. So these two guys here, they are not equal. Okay? Which means, as a whole, so limit negative 1 to the n squared over n squared plus 1 as n approaches plus infinity, this does not exist. Thus, by divergence test, okay, the series negative 1 to the n squared over n squared plus 1, and from 1 up to plus infinity is divergent. Okay? Questions?